All right. Thank you everybody for joining us again. The topic of today will be welding processes. So if we follow the progression we had so far in the class, after a brief introduction to welding, then we discussed joining at large. And we discussed from riveting to bolting to nailing to staples to welding. And we said welding is a small subset of joining processes. And then we discussed a little bit more about what did we do last class? Gosh, well, so and now we are going to discuss about the welding. We discussed terminology, and that was like learning a whole dictionary. We discussed symbols, and now we're going to get into fusion welding, and in particular, arc welding. And within arc welding, we're gonna see that there is still a huge diversity of processes for arc welding. And I want to start with the arc welding processes in which we have a non-consumable electrode. So in this type of processes, the electrode is not supposed to melt. But before I tell you the details about this process, let me tell you a little bit about the history of this process. So here we have this image of a very weird plane, right? It's a plane that kind of has no tail, the engine, the propeller is backwards, but there's more crazy stuff about this. This plane, it's made out of magnesium. And this comes from an effort during World War II in which there was scarcity of aluminum. And then the Americans, everybody, but the Americans in this case, were looking for alternatives to aluminum. And of course, magnesium is very light. Magnesium would be a very bad idea for making planes because it's very prone to corrosion, not to mention that it's quite flammable. So even if the plane flew fine, I'm not too sure I would want to step on it. But they went ahead and they said, okay, we are short of aluminum, how about magnesium? And while we are thinking about crazy materials for this airplane, let's think about crazy processes. How about if instead of riveting, we weld it? Sure, at the time, and this is just after people were welding the Graf Spee, this battleship I mentioned to you, and about the time in which the T-34 tanks were welded. The way of welding, if it was not submerged arc welding, would be stick welding. But magnesium is so reactive, it doesn't work with stick welding. And they thought, what can we do? And they thought of a derivative of, oh, but by the way, before I tell you about the details of the process, there's one more detail about this plane. This plane was not meant to carry guns. This plane, and here is a second incarnation of the plane from right after the war, in which they were planning on using jet engines. The idea was that this plane would ram into the tail of a bomber and destabilize the bomber and make it crash. And this drawing I have here is pretty funny because they put it as if it was the Germans trying to destroy the American planes. No. It was the Americans trying to destroy whoever's bombers, and after World War II would be the Soviets, by ramming them. Right, and here in this initial design of this plane, the pilot lies prone. So now you can imagine on a jet plane going full speed, head first, like skeleton in the Olympics, into the tail of a plane. Sounds kind of crazy, right? And of course, it didn't catch on, and this plane was never made in series. But however crazy this plane is, right? Some kind of American kamikaze, right? However crazy is because of these planes that people thought, how can we weld magnesium? And the way they decided to go was with the derivative of carbon rod welding, and is what today we would call gas tungsten arc welding, or TIG. It was invented for this process. And when we talk about the physics of the arc, we're going to see so many interesting things. But among those is that because these materials have a high thermal conductivity and suck up the heat very quickly, they wanted to have a lot of heat put in. And we're going to see that to have more heat in the weld, you can use helium as a shielding gas, and makes it very hot. And originally, this process was called heliarc, right? Kind of a funny name, as if it was like a helix of a propeller, right? Like helicopter. Well, heliarc, because it was helium, and this tungsten rod was made for welding crazy planes, right? Right today, nobody welds crazy planes with TIG, but we do a whole lot of things with TIG. And I want to start discussing welding processes with TIG. And it's paradoxically, to learn to do TIG by hand is among the most difficult welding processes. Typically, if you go to a place like MatE or through some welding training, that's what they are going to teach you last. Now, despite that it's very difficult to do by hand, for us in engineering, it's the easiest one to explain. So I want to start with TIG because it's the one for which I'll have to name the fewer amount of components. And then we are going to increasing the complexity of the welding processes we discuss. So on the right, we have some photos of what a TIG torch looks like. And here is a handle. Here we have this thing that looks like a pencil tip that is pretty sharp and shiny. I'll tell you more in a second. This is like a whole rod, right, that goes in. And here we have this schematic. And the schematic has only what we need to know at this stage. And it is this. Number one, you have this rod that looks like a pencil tip. This rod is made out of tungsten because tungsten has two important properties. One is that it has a very high melting temperature, so it's not going to melt. And two, and for whatever reason that is what is called a thermionic material. And that is unrelated to the high melting temperature, but it's very convenient. And what it means is it can lose electrons very easily in certain circumstances, which we will discuss later. But now we have a material that can take the heat and can give me electrons to start the electric circuit of having the electrons going through the gas. So the distance between the tip of the tungsten and the surface of the weld pool, that is what is called the arc length, right? And so if I pull the tungsten back, I would have a longer arc length. If I push the tungsten in, I'm gonna have a short arc length. Typically in TIG, the electron is negative, which means when this is negative, the electrons will be jumping out of it. And because it's a thermionic material, it's convenient, that is tungsten, and it has some advantages. And when we study the physics, we are going to see that this makes a lot of sense. The other side of the electrical circuit, the electrons jump out of the cathode and land into the other part of the circuit that is called the anode. And we're starting to introduce more names into our dictionary of welding. Electrons jump out of the cathode, land into the anode. This little rod here is the filler. So we are introducing, sometimes the weld has no filler and would be autogenous. Sometimes you would have a filler, and you put the filler with a wire. You can hold the wire with your hand, or you can have the wire unspool semi-automatically, similar to the MIG process, for example. Now, there is something interesting. Steel or aluminum, most metals are very reactive with the oxygen in the air. Some are also very reactive with nitrogen. Well, that's a problem. So how do we prevent the hot metal in liquid state at 1500 degrees or more, 2000 degrees C, from reacting with this oxygen? There are many ways. The way we use in TIG, and it's the simplest, is we blow some amount of inert gas, a noble gas. Could be argon, could be helium, could be many other things like krypton if we want there. But we don't want because it's too expensive. But argon is distilled from the atmosphere, so it's relatively cheap. Helium is a non-renewable resource and it's a lot more expensive, but those two are available. And we blow this inert gas, and this will protect the surface of the molten metal from being in contact with oxygen or nitrogen. And the nozzle through which it goes, we call the shielding cup. I marked it here as F, and it's this pink thing we see here. Those tend to be made out of ceramic. We're gonna see that the similar thing in MIG is made out of metal, but in TIG is ceramic, right? Here we have our base plate, and here I indicated the weld pool too. This comes from an exam. An interesting thing for TIG as well as for MIG, in North America, we have this kind of formal name. In the case of TIG is gas tungsten arc welding. So the arc welding is because we have an arc, and we're gonna see it appears in pretty much all arc welding processes. The gas is because it's gas shielded. The protection from the atmosphere is through a shielding gas. And T is because of the tungsten electrode, right? And although we write GTAW, some people would call it GTAW, right? Most of the time we are gonna say TIG. That is the very old name, and is what the Europeans still use. That means tungsten inert gas. So in welding, we have this funny thing in which things have a proper name, which we can use in writing, but it's not what we use in speaking. So if I say TIG, or if I say gas tungsten arc welding, or GTAW, or GTAW, it's always the same. And neither me or anybody else is trying to confuse people by shifting from one name to the other, but it happens, and we will need to accommodate. So here's a little bit summary of what I was talking about. The way we protect the molten metal is with an inert gas in this case. Typically is argon. If instead of argon, we would have something that is reactive, like a little bit of oxygen, this would react with the tungsten and ruin the tungsten, because tungsten is also very reactive. The filler metal that is coming here, if we put none, is autogenous. If it is external, could be homogeneous or heterogeneous, as we already discussed. And the way we add the filler can be manually, and I'm gonna show you a video of how it goes. You put the filler metal manually, or it could be automatic. And if it is automatic feeding, the wire can come in just as it is here, that the wire is not part of the electrical circuit, and you melt it with the arc, or you can have the wire touch the melt, and with a secondary power supply, you can preheat it using resistor heating. This is what is called hot wire, which we'll discuss in a second. In arc processes, polarity matters. So typically TIG welding, gas tungsten arc welding, is run at constant current, which means the machine will give me more or less the same amount of current, say 125 amps. And if I move the electrode farther or closer, it's gonna be 125 amps. The voltage is going to change, but the amps are gonna be more or less constant. And this is intelligent, because the strength of the arc is given by the current. So if I always have the same current, the arc is going to have always the same strength. And I can use the TIG almost as if it was a brush, of which the bristles have always the same stiffness. Polarity is typically electrode negative. However, when we weld aluminum, we tend to use, the best to use is variable polarity, or AC, alternate current, in which sometimes is positive and sometimes negative. And in some cases, we might use the electrode as positive, as the electrode would be an anode, right? That's not very common, but is often used in aluminum because aluminum has this hard oxide layer. When we think aluminum doesn't rust, it's not true. It oxidizes very quickly, but this oxide is very protected. It's not like iron oxide that is not protected. So this layer of aluminum oxide prevents from further corrosion. When we want to weld that, this layer of oxide is a problem, and is making the weld more, is contaminating the weld and making the arc unstable. But if we use variable polarity, when the plate is negative and the electrode is positive, which is the opposite of normal for TIG, in that case, for reasons that are not very well understood, some people say it's because the electrons spoil off the oxide layer. Some people say that the impact of the ions destroy the oxide layer, but for some reason there is cleaning, and the more electrode positive, the more the plate is negative, the more clean it is in aluminum. So that is an interesting thing. Characteristics of TIG requires a very high manual skill. I know we have at least 2 TIG welders in this class, and I'm not going to interrupt for that, but if we were all in the class, they could tell you firsthand how this is not for the faint of heart, because you need to have a really good hand. But this can make very sophisticated welds. So when we say TIG, would be like the equivalent of a scalpel for a surgeon. It's something that can make very precise cuts. You wouldn't be chopping down a tree with a scalpel, right? You'll use a chainsaw, but you would not do surgery with a chainsaw, I want to believe. So this is the scalpel. Make small, very sophisticated welds. And where do you use it? Race cars, most welded parts are TIG welded. Suspension parts, for example. Jet engines, rocket engines, those are TIG welded, right? It's small, sophisticated, slow, but very detailed and very precise. It's a high purity type of weld. This is among the most pure welds you're going to get in a shop. That has very low amounts of contamination, has a very low amount of fume generation. It's good for heat sensitive materials too, because of these small welds it makes, but it's not a high productivity process. Applications: shop welding and root passes in pipes in shops. For example, when you make a pipe, and we discussed on Tuesday, the first pass is the root pass, and it's very, very important. In many cases, those root passes are done with TIG welding, right? In which we can bridge this gap without burning too much. But we are not likely going to see, seldom, TIG welding in the field. And the reason for that is the protection of the molten metal is a shielding gas. It's this argon flow, maybe helium. In a shop, we're fine, but if we are in the field, and if it is a draft, the draft of the wind in the field might blow away my shielding gas, and all of a sudden, the molten metal would be exposed to oxygen and nitrogen. And in the case of TIG, it's especially bad because also the tungsten might be exposed to oxygen, so everything gets ruined. So if we want to use processes that have a shielding gas, like TIG in the field, typically they make a shack around it to prevent drafts. And even if you make a shack, somehow where I heard these drafts still somehow come in. So this TIG much like all other gas shielded processes, tend to be shock processes and less common in the field.
Gas tungsten arc welding.
Hold on a second. Okay, so I want to see. Okay, good. So I have a video that is mostly aimed at welders, but it's an introduction to gas tungsten arc welding. I'm gonna play it for you, and I believe you should be getting the sound okay through this. So let's go here and here.
Gas tungsten arc welding uses a non-consumable tungsten electrode and externally supplied inert gas shielding. The most common shielding gases used are argon and helium, and mixtures of the two gases. All types of steels and most non-ferrous metals can be welded in all kinds of joints and positions. Depending on the application, workpieces can be welded without a filler metal or welded with a filler metal supplied separately to the joint. The gas tungsten arc welding process employs either an alternating current or direct current power source, depending on the type of metal to be joined and its thickness. Some power sources provide pulsating direct current with variable frequency. These adjustments allow better control of the molten weld metal when welding thin sections and when welding in other than the flat position.
All right. So that was a general introduction to welding, where you got to see some images of the welders. In some cases, they were putting autogenous without filler. In others, they had this rod, and this rod is the filler they were putting in. None of those processes you saw use a automatic feeding system, neither cold wire nor hot wire. So you saw autogenous or you saw a manual feeding. Now I want to show you some videos we did take in the lab about TIG and the effect of the different gases and pulsing. So let's start with argon. So this is where a TIG weld looks. In this case is automatic welding. So the torch is held by a machine. And this looks like a photo, but in reality it's a video, right? And if you pay attention, you're gonna see how the torch is moving to the right, but we did it at high speed. So it looks like it stopped. This is the argon arc. Here we have the electrode. Down here we have the plate. Right under the arc, we have the weld pool, and this very bright part is the arc. Now, as you saw in the previous video, it talked about pulsing in some cases. And when I showed you the images of weaving, I mentioned one of the weaves had something called a stack of dimes. And I mentioned that this happens because as you move the torch is pulsing, and essentially it's kind of creating a sequence of spot welds, one after another one. So let me show you what it looks like when you pulse the weld. There you go. So you can clearly tell when the current is high and when the current is low. We have this small arc and then this big arc, right? And what is happening in this case is creating kind of a sequence of spot welds. The other thing I wanted to show you here is the effect of the gas. We talked about argon and helium, or a mixture of the two. So let's talk about what happens if you use 100% helium. In our lab, we can do pretty much everything. We have a computer-controlled mixer that can mix up to 4 different gases at the same time. So when the lab reopens, if any of you wants to do some research, we could expand these videos to have those different mixes. Okay, let me show you helium now. And I'm gonna turn this on too, so you compare it with argon. It's a very different arc. You're gonna see it now. Look at this. Argon is kind of this concentrated arc, and helium is kind of this broad, ghostly arc. Isn't that interesting? When we talk about the physics of the arc, you're gonna see that helium also gives you a much higher voltage, much higher heat, right? And here, let me show you how it looks when the helium is pulsed. There you go. High current, low current. You see how the spot welds are formed? When we talked about the stack of dimes, right? Is what we are talking about, these circles that are built every time the arc is hot. I want to tell you a little bit about something interesting. We talked about the shielding gas. And the shielding gas, like argon, is supposed to cover the molten metal and push away all the air that has oxygen and nitrogen. Now, if this gas has turbulence, then the turbulence would start entrapping, would entrap some of the air, entrap oxygen, entrap nitrogen, and have even if a small amount of those gases mixed with the argon, and those would react with the weld, and you would have a weld with porosity and defects. What people figured out is that these issues of fluid mechanics, out of the torch, the gas comes in a turbulent state. So here you have a torch that is put horizontal, and you get to see how the argon, which is heavier than air, how argon is creating some turbulence. This turbulence brings in oxygen and nitrogen. But they put something which they call a gas lens. And a gas lens has absolutely nothing to do with the lens like in the glasses. I don't know why they call it a glass lens, a gas lens. I don't know, but they call it a gas lens. And what it does is to kill the turbulence of the gas and have what is called, all of you have taken fluid mechanics, a laminar flow. So what you get to see here is how the gas is coming out quite straight. Laminar flow, that's exactly what we want. And if the distance is too high, then turbulence sets in and we can have a problem. Here you have another image of the gas lens. A gas lens is, if ever any of you ever was exposed to wind tunnels testing race cars or things like those. In a wind tunnel, you have a fan, and between the fan and the scale model you're testing, they have a series of kind of baffles that get the air very, very straight. Very straight. It's like fins. And that makes the laminar flow. That's exactly what a gas lens is. When you open it up, the torch, you get to see how it has these like little passages to make the air laminar. In this slide, we see a couple of things that are very, very interesting. We see two things that are interesting. One, and both relate to this effect of seeing that the gas starts as laminar and eventually becomes turbulent. So what do we see? Number one, if I were to have too long of an arc length, the gas would become turbulent and would entrap gas, right? So a long arc length can be a problem for that. And the second thing we see is that if we were to put too much of a flow of gas, if we say, oh, I want this to be really well shielded and I don't care about money, I'm gonna crank up my argon to 110. And you crank your argon to 110, and all of a sudden your weld is worse, because if you have high flow, you can have turbulence, and the turbulence, even if the arc length is small, would capture some amount of oxygen and nitrogen. And these two things can be explained based on the Reynolds number. All of you were exposed to that in fluid mechanics. In the Reynolds number is, if we have a high Reynolds number, we have turbulence. and low Reynolds number is laminar flow. And the Reynolds number has on the top velocity and length. So what do we see? That if we increase the length, Reynolds number would be higher. If we increase the velocity of the gas, Reynolds number would be higher, right? So an important lesson from this course you're taking is if you want really good shielding, you don't necessarily need to put more gas. If you have too little gas, you need a little bit more gas. But once the gas is right, if you have problems of shielding, you do not solve them by increasing the amount of gas. For example, if you're doing a weld with very high heat input, that means it's going to take very long to cool. That means that you might have moved past the weld before it's solidified, and then the tail of the weld might still be liquid and react with the oxygen. In that case, you would use a trailing shield, but you do not increase the flow of gas. When I mentioned how you feed a consumable into TIG, I mentioned can be manually or can be semi-automatically through a spool of wire. If you feed through a spool of wire, it can reproduce the manual process of putting the wire in, or I mentioned it can touch the weld pool. So we have this very old drawing here from a patent from a guy I know, Gus Mans, that is the engineer who was in charge of the AWS welding handbook for many years. So look at this. In this schematic, we have a power supply, and the negative side goes to the electrode. This is our tungsten electrode. Here we have our plate, and here we have our arc. So far, this is exactly what we have been discussing. Now we have this spool of wire that is unspooling and bringing wire to the weld, more or less like you would expect. But here's the interesting thing of this patent, and it's a huge, very important invention. What they do is that the wire touches the melt, and now they have a secondary power supply. Secondary power supply, and you have a circuit. And that means that you're going to have current flowing between this contact tip that is touching the wire, and the wire is sliding relative to this contact tip T. And in this part between the just outside the copper contact tip and the work, you're circulating current through a piece of wire, which is a resistor. And if you do it right, the wire is going to get to the weld pool already at the melting temperature. Now, here is a huge paradox. The hot wire process gives you the coldest possible weld. Isn't that crazy, right? The hot wire gives you a cold weld, and this is why. If I'm doing TIG and I want to add filler metal, I need to melt this filler metal, and it's not easy to melt. So I need to put extra heat until it melts. That is slow and that is hot. By the time a droplet of wire comes into the weld pool, I have put already too much heat in the weld pool and in the wire. But in the hot wire process, I'm putting the wire right at the melting temperature, 0 superheat. And I can put a lot of wire. So I can make a weld that is relatively big, a big cross section. But the amount of heat I put into that weld is just the mathematical minimum to put the melting in, right? So this, the heat input in this case would be relatively low despite the large cross section. So here's the paradox. Hot wire can give you a cold weld. When do we want cold welds? For example, in stainless steels, we don't want the weld to get too hot or to take too long to cool down, because if the stainless steel can sensitize, hot wire is a really good technique for that. Let me show you a video of a hot wire done in our lab. Here we have our tungsten electrode, and by now you see, 2 days ago, some of you didn't know what TEG meant. Now we're talking about the subtleties of the electrode. The arc is coming in here. Here we have the weld pull, but the interesting part is this you see here on the left. And you see it's kind of faint, but you see it's somewhat lighter, an amount of wire that is coming in. And you see how it's melting in? There's another interesting thing. Look at this. Look at the arc at the tip. Do you see how this arc is moving? Does anybody want to tell me through the chat, why do you think this arc is moving? It's moving periodically. Anybody wants to venture a guess? Somebody suggested gas interference, but no, there is no problem with the gas. Gas has no issue. There is no wind here, nothing. Yes, somebody suggested the current being pulsed. Now we have two currents. We have a current at the tungsten electrode and a tungsten current in the wire. Which one would be pulsed? So somebody suggested there is a waveform. And yes, there is a waveform, but in this case, it's a very simple waveform that is a square wave. And the one that is pulsed is not the, is the wire in this case. It's, well, it's just the other way around. The tungsten is pretty much DC as usual, DC electrode negative. And this is a unit, which we still have in the lab. It's a unit from Japan. And this pulses. And this pulsing is part of their patent, because if there is, if this contact breaks, you couldn't circulate a current, and we would have a problem. So this is a really interesting process. Yes, and the reason the arc moves is because we have an electromagnetic interference between the magnetic field of the wire with the magnetic field of the tungsten. This is very interesting, very interesting. So when the current circulates through the wire, it pushes the TEG to the side. We're gonna talk a lot more about these interactions later on when we discuss arc flow and multiple electrode welding. Okay, a very quick question before we move on. TEG uses a consumable electrode. True or false? Yes, thank you. False. It's false. Funny enough, eventually you have to replace the tungsten electrode. So some people could argue it is a consumable because in the end you consume it. But this is called right. But although, yes, so does the shielding cup need to be replaced after it gets used too, after a while. But as you weld, you don't expect any tungsten to end up on the plate and or anything else. So TEG is the simplest process. The tungsten is there, in theory is there forever. In practice, it's not there forever, but this is not supposed to melt. And the only thing that melts is the base plate and maybe whatever wire or rod we're putting in. So let's move it up one notch. And I'm going to tell you a process that now has such focused heat. And as we talked in our second lecture, focused heat means moving faster. And if you move too fast, you cannot do it by hand. And that's the case of plasma arc welding. And in this case, I'm talking about plasma transfer arc welding. There are two types of plasmas. This plasma transfer arc welding, the current transfers from the tungsten electrode to the base plate. So in reality, PTA or plasma arc welding does not look at all like TIG or like any other welding processes. We have it in our lab. You'll see videos, and I hope one day you'll see the machine in action. But from the physics point of view, if we explain the mechanisms, plasma is very similar to TIG. We have a tungsten electrode, we have the plate, we have a shielding cup, and we have a shielding gas. All that is the same as TIG, but there is a difference. And the difference is that while in tungsten, the arc was free to expand, but in PTA, the arc is not free to expand. We have a jet of inert gas, a secondary jet of inert gas that is constricted. So now the arc, if you remember our very first lecture, we talked about how the arc creates a jet because of electromagnetic currents. We'll discuss that more later, but we do know there is a jet, and that jet, those of us who have welded, you know that that jet can even push the molten metal away, right? In the case of PTA, this jet is very concentrated. So it's even finer than the scalpel, right? It's very, very, very fine arc. And for that reason, it's very, very hot. But now our equipment is more expensive. We have all the expenses of TIG, plus the expense of having a second gas flow, that is the flow that constricts the TIG. And the torch doesn't look like a TIG torch at all, because it has this extra conduct, right? This extra conduit for the primary gas that makes the arc. In this province, we use PTA to make overlays, and overlays means not putting two things together, but depositing metal on top of other metal, such that we coat the whole metal, for example, with something that is corrosion resistant or wear resistant. And how do we deposit this other new metal on top of the base metal? Typically with powder. So we blow powders and we melt them with the arc, which means a PTA torch has some holes, and through those holes, we blow a third flow of gas. And this third flow of gas is called the carrier gas, and has metal powders in it, and those metal powders get deposited. So PTA typically is a non-autogenous process. And the type of powders we put, because they are either more corrosion resistant than the base metal, or because they are more wear resistant than the base metal, typically this is an heterogeneous type of process. Very interesting. So from the point of physics, very similar to TIG. From the point of engineering and its mechanisms, very similar to TIG. From the point of view of practice, very different. But I wanted to bring it up. This is a process that we do a lot in this province. We have a question that says, does this have to do with laser cladding? And the answer is, in many aspects, this is just like laser cladding. In laser cladding, we also have a carrier gas that deposits powders, but the heat in laser cladding is the laser, and in this case is the arc with the tungsten. There's another important difference. In laser cladding, the laser tends to be quite a far back from the weld, because it's just light being projected as long as you get the focus somewhere around the weld pool. In PTA, because you have an arc, you're forced to have a given arc length that would work with the system. So in this case, your torch has to be quite close to the component. But yes, similar to laser cladding, you can do additive manufacturing with PTA too. So for PTA, shielding is an inert gas, typically argon, just like in TIG. Filler material, typically heterogeneous, as we discussed, or corrosion protection. If we have no filler, is what we call plasma arc welding, right? And if we crank up the current too much, it becomes plasma cutting. All the same thing. The polarity of PTA is much the same polarity we have seen in TIG, typically constant current electrode negative. Very similar to TIG, we mentioned it can create a keyhole. Remember when on the second class about terminology, I mentioned keyhole, and I said how using cellulosic electrodes give you something that people call a keyhole, but has nothing to do with the keyhole of lasers or electron beams. But PTA or plasma arc welding start getting into the league of keyholes of lasers and electron beam welders, because they have this very concentrated arc. They must be mechanized or automated because the arc is too small to be used by hand. You need to move too fast. Can make welds that are smaller than GTAW, smaller than the scalpel, but it's not as small as a laser or as an electron beam that can make even finer welds. High purity, just like TIG applications, mining, oil and gas for overlays, for wear resistant and corrosion resistant overlays. In this province, we use it a lot to make nickel tungsten carbide overlays that are very sensitive to heat. And if you use other type of welding processes, you can dissolve the carbides.
In plasma arc welding, metal coalescence is produced by a constricted arc made up of a high-velocity stream of ionized gas called a plasma. In most plasma arc welding operations, the plasma jet is generated by heating the orifice gas in the torch polenum chamber to a plasma and forcing the plasma to exit through a constricting nozzle or orifice. Partial shielding is obtained from the plasma and is supplemented by an auxiliary shielding gas. Auxiliary shielding gases used include argon, helium, or mixtures of argon with hydrogen or helium. Because of the constricted arc, the heat energy of the plasma stream is concentrated and extremely intense. This permits deep penetration, narrow welds, and rapid welding speeds with good arc stability. Workpieces can be joined with or without filler metal. Plasma arc welding can be used to join most ferrous and non-ferrous metals, including extremely thin materials such as foils. Plasma arc welding equipment cost is high, however, so the process is often limited in its application.
Something interesting that the video mentioned is you can have argon, helium, some mixtures of the two. I also mentioned hydrogen. How interesting. So our PTA machine in the lab, for example, has an inlet for hydrogen, which we never use. Oh, here is the question. So if we could weld with a plasma cutter, if we turn the energy output down, the answer is yes. Now, if you wanted your weld to be any good, probably you would not be doing that, right? There is a reason why they designed as a plasma cutter, and a reason why you make a welding. When you do cutting, often you blow air to oxidize the material and to help the cut. So in addition of putting the power down, you would need to cut down the blowing of air and replace it with some sort of inert gas. But yes, in principle, the cutter or pretty much any other heat source can be considered for welding. We already talked about using the energy of the sun for melting metals, and I uploaded a couple of articles. Let me tell you one more. In the US, for a while, they thought of using electron beams to shoot down incoming missiles for ships, right? And they can be a big problem. And they made an electron beam that could shoot the electrons far into the air. And there are reasons why the electrons like rip off the air and concentrate themselves, but didn't go straight. So this very high energy electron beam was not good for shooting down missiles. But guess what? With that much power, they decided, let's try it for welding, right? And of course, and people could make some welding with very interesting properties. With a very high voltage, the electrons were causing heat that was below the surface. That was done in Lawrence Livermore National Lab. Very interesting. So yeah, if you find any source of heat that is intense enough, people will think, how can we use it for welding? All right, let me show you some videos of PTA. These are videos from our lab. What do we see here? Here at the bottom, we see the plate. This is the clad that is being deposited. What we see here is the powders, because this is at a little bit more than 4,000 frames per second. We see the powders coming in, and you realize the powders are coming in very fast. And these are the powders that get melted in with the arc, and they melted by the high temperature of the weld pool. You get to see also how some of these powders bounce off, right? And that is what is called catchment efficiency. Whatever stays in the melt that is caught by whatever it goes to the side, but bounces off and is lost. And typically, it's not good because it's contaminated. Let me show you another video. In this case, we are using how many frames per second? 10,000 frames per second. And what do we see? So this is about twice the frame rate of the video on the left. And we see the torch is moving. Here is the plate. Here is the arc. And we see the powders coming down. And we see some, but because of the catchment efficiency is less than 100%, they fly away. Right? You get to see that this is quite different than TIG. Although the physical mechanisms, the engineering is much the same. All right. Anybody wants to venture a guess for this? PTAW competes with laser for some cladding applications. You're so right. All of you are so right. Absolutely, absolutely. PTA can create this very narrow heat source that competes with lasers. Now, here's the funny thing. Although PTA can compete with lasers in many aspects, lasers require such a high level of automation that typically a laser operation has often been preferred over a PTA just because those people in the laser are so careful and so automated. But in many cases, PTA could do it too. Right now in our province, we have 4 laser cladding outfits, and we have many, many more outfits doing PTA. Now with the low oil price, I'm not too sure how many of those are gonna stay standing. But in our province, we have one of the highest concentrations of PTA machines in the world, and also laser cladding in the world. We are fortunate. We are in a place that is extremely advanced worldwide for using this type of technologies. All right, so this was about consumable, non-consumable electrodes. what I'm going to do is now I want to shift and talk about welding processes in which we consume the electrode on purpose. I'll stop sharing here. And we're gonna go here.